All right, so this is CS50, and this is week 2, wherein we're going to take a look at a lower level at how things work. And indeed, among the goals of the course is in this bottom-up understanding, so that in a couple of weeks' time, even a few years' time, when you encounter some new technology, you'll be able to think back, hopefully, on some of this week's and this course's basic building blocks and primitives, and really just deduce how tomorrow's technologies work. But along the way, it's going to be a little hard, perhaps, to see the forest for the trees, so to speak. And so the goal at the end of the day still is going to be problem solving. And so we thought we'd begin today with a look at some of the problems we'll talk about or solve this coming week. And for that, we have some brave volunteers who have already come up. If we could turn on some dramatic lighting and meet today's volunteers. So on my left here we have...
Hi, my name is Alex. I'm a first year at the college, and I'm from Chapel Hill, North Carolina.
Welcome to Alex. And to Alex's right?
I'm Sarah. I'm from Toronto, Canada, and I'm also a first-year student at the college.
Wonderful. Well, welcome to both Alex and Sarah. So one of the problems you'll perhaps solve this week for problem set 2 is to analyze the reading level of a body of text, whether someone reads at a first grade level, second grade level, third grade level, all the way up to 12 or 13 or beyond. But you've perhaps never quite thought about, certainly in terms of code, like how you would analyze some text, some book, and figure out what reading level is it at. And yet surely our teachers growing up kind of knew or had an intuitive sense of this. So let's consider some sample text. For instance, Alex, what have you been reading lately?
1 fish, 2 fish, red fish, blue fish.
Wonderful. So given that, what grade level would you say Alex is currently reading at? Feel free to just shout it out. First. So indeed, you'll see this week, if you run your code on Alex's text, it actually turns out he reads below a first grade reading level. But why might that be? What might your intuition be for why we've accused Alex of reading at this level? Feel free to shout out. Yeah, so very few syllables, short words, short sentences. And so there's some heuristics, perhaps, we can infer from that short text that probably means that it's best for younger children. Now, Sarah, by contrast, what have you been reading?
Mr. and Miss Dursley of number 4, Privet Drive, were proud to say that they were perfectly normal. Thank you very much. They were the last people you'd expect to be involved in anything strange or mysterious because they just didn't hold with much nonsense.
All right, now irrespective of what grade you were in when you might have read that text, what grade level does Sarah seem to be reading at? So 8th grade, 2nd grade. OK, so hearing a bit of everything, so that, at least according to code, would actually be 7th grade. And what might the intuition there be? Why is that a higher grade level, even though we might disagree exactly which grade it is? Yeah, so complicated sentences, longer sentences. So indeed, a lot more words were being spoken by Sarah because there was so much more there on the page. So we'll translate these ideas this coming week in problem set 2, if you tackle this one, to code so that you can ultimately infer things of these quantitatively. But to do so, we're going to have to understand text. So let's first thank our volunteers, and then we'll dive into that lower level. Stress balls. You can keep those, yeah. All right, so besides that, let's consider one other body of text perhaps that you might see this week, which is namely a little something like this. What I have here on the screen is what we'll start calling today ciphertext. It's the result of encrypting some piece of information. And encryption, or more generally the art and science of cryptography, is all around us. It's what you're using on the web, on your phones, with your banks, and anything that tries to keep data secure is using encryption. But there's going to be different levels of encryption, strong encryption, weak encryption, and what you see here on the screen isn't all that strong, but we'll see later today how we might decrypt this and actually reveal what the plain text is that corresponds to that ciphertext. But in order to do so, we have to start taking off some training wheels, so to speak. And believe it or not, even though your time with C this past week, for the first time probably, might have been rather in the weeds and much more complicated seemingly than C, it turns out that along the way we have been providing and will continue to provide certain training wheels. For instance, the CS50 library is one of them, and even some of the explanations we give of topics for now in these early weeks will be somewhat simplified, abstracted away, if you will. But the goal ultimately is for you to understand each and every one of those details so that after CS50 you really can stand on your own and understand and wrap your mind around any future technologies as well. So let's consider first the very first program with which we began last week, which was this one. So hello world in C. At the end of the day, it was really the printf function that was doing the interesting part of the work. but there was a lot of technical stuff above and below it. The curly braces, the parentheses, words like void and include, and then, of course, the angled brackets and more. But at the end of the day, we needed to convert that source code in C to machine code, the zeros and ones in binary that the computer understood. And to do that, of course, we compiled the code. We ran make, and then we were able to actually run that code there. So let me actually go over here to VS Code and really quickly recreate that hello.c, pretty much by transcribing the same. So I might have here include standard io.h, int main void. And then in here, I had quite simply hello, comma, world with my backslash end quotes and more. Now, last time to compile this, I indeed ran make hello followed by enter. Hopefully, you see no errors, and that's a good thing. And if you do /hello, you see, in fact, the results of that program. But it turns out that make is not actually a compiler, as I alluded to last week. It's a program that clearly makes your program, but it itself just automates the process of using an actual compiler. And there's lots of different compilers out there. And the one that it's actually using underneath the hood is a little something called Clang for C language. And Clang is a pretty popular compiler nowadays. There's another one that's been around for ages called GCC. But these are just specific names for types of compilers that different people, different companies, different groups have actually created. But if you use, in week 1, a compiler yourself manually, you have to understand a little more about what's going on, because it's even more cryptic than with just make alone. So in fact, let me go back to my terminal window here. Let me go ahead and clear the screen a little bit and just run really the raw compiler command. So what make is automating for me, let me actually do this manually for just a moment. So if I want to compile hello.c into an executable program I can run, I can do this. Clang space hello.c and then enter. And now there's no output, which is a good thing. In this case, no errors. But notice this. If I go ahead and type ls, it turns out there's a file that's been created suddenly in my current folder, weirdly called a.out. That stands for assembler output. And long story short, that's actually the default name of a program that's created when you just run Clang by itself. Now, that's a pretty lame name for a program. It's a pretty that's a pretty bad name for a program because it doesn't describe what it does. So better would be here to perhaps do, well, instead of a.out, which, yes, still prints hello.world, but isn't really a clearly named program, it'd be nice to name this hello. So what could I do? I could do like we learned last week. Well, I could rename a.out to hello by using Linux's mv command. So I'm going to move a.out to become hello. But that, too, seems kind of tedious. Now I have 3 steps, like write my code, compile my code, and then rename it before I can even run it. Like, we can do better than that. And so it turns out that certain commands like Clang support what we're going to start today calling command line arguments. A command line argument, unlike an argument to a function, is just an additional word or key phrase that you type after a command at your prompt in your terminal window that just modifies the behavior of that command. It configures it a little more specifically. So what you're seeing here on the screen is a summary of a better command with which to run Clang, so that now I can specify the output of this command per this -o. So what do I mean by that? Well, let me go ahead and clear my terminal window again and more explicitly type Clang -o hello.c and then enter. Nothing, again, appears to happen, but that's a good thing when you see no errors. And now the program I just created is indeed called hello. So it achieves really the same exact effect as make did, but what I don't have to do with make is type and remember something as long as this command. And this, too, is a bit of a white lie. It turns out we have pre-configured VS Code in the cloud for you to also use some other features of Clang that would be even more tedious for you to write yourselves. And so really, this is why we distill this as ultimately just running make. So let me pause here to see first if there's any questions on what I've done by taking my very first program in C and just now compiling it first with make, but then starting over and now manually compiling it with Clang with what we'll call command line arguments, -o space hello, and then the name of the file. Yeah? Yeah, so a.out is a historical name. It refers to assembler output. More on that soon. And it's just the default file name that you get automatically if you just run the compiler on any file, so that you have just a standard name for it. But it's not a very well-named program. Instead of running Microsoft Word on your Mac or PC, it would be like double-clicking on a.out. So instead, with these command line arguments, you can customize the output of Clang and call it hello or anything you want. Other questions on what I've done here with Clang itself, the compiler? Yeah. So -o, and you would only know this from reading the manual, taking a class, means output. So -o means change Clang's output to be a file called hello instead of the default, which is a.out. And this, too, is, again, a detail you would have to look it up on a web page, read the manual, hear someone like me tell you about it. And in fact, there's even more than these options. But we'll just scratch the surface here. All right, so if we now know this, what more is actually happening underneath the hood? Well, let's take a closer look at not just this version of my code, but my slightly more complicated version last week, which looked a little something like this, wherein I added in some dynamic input from the user. So I could say not hello world to everyone, but hello David, or hello to whoever actually runs this program. So in fact, let me go ahead and change my code here in VS Code just to match that same code from last week. So no new code yet. I'm just going to, in a moment, compile it in a slightly different way. So I did last week string, I think answer equals get string, quote unquote, what's your name, just like in Scratch. And then down here, instead of doing world, I initially wrote answer, but that didn't go well. What did I ultimately do instead to print out hello David or hello so-and-so? Yeah. Sorry, a little louder? Yeah, so %s, the so-called format code that printf just knows how to deal with. And then I had to add one other thing, someone else. Besides %f, yeah. The name of the variable that I want to plug into that placeholder %s. And in this case, it's answer. Now, let me make one refinement, only because now we're in week 2, and we're going to start writing more lines of code. Even though Scratch called the return value of the ask puzzle piece answer always, in C, we have full control over what our variables are called. And now it's probably good not to just generically always call my variable answer if I'm using getString. Let's call it what it is. So this is now just a matter of style, if you will. Let me change the variable to be named, just so that it's a little clearer to me, to you, to a TF or TA, exactly what that variable represents, instead of more generically answer. All right, so that said, let me go down to my terminal window. And last week, again, I ran make to compile this exact same program. Now, though, let me go ahead and just use Clang. So Clang -o, I'll still call this version hello, space hello.c. So exact same command as before. The only thing that's different is I've added a couple of more lines of code to get the user's input. Let me hit enter. And now, darn it, our first error. So output from Clang and make is not a good thing. And here we're seeing something particularly cryptic. So something in function main, undefined reference to getString, and then linker command failed with exit code 1. So there's actually a lot of jargon in there that we'll tease apart today. But my hint is that clearly my problem's in main, although that's not surprising because there's nothing else going on here. GetString is an issue, and the issue is that it's an undefined reference. And yet, notice, I was pretty good. I added the CS50 header file, and I said last week that that's enough to teach the compiler that functions exist. But the problem is that even though this does, in fact, teach Clang that getString exists, it is not sufficient information for Clang to go find on the hard drive of the computer the zeros and ones that actually implement getString itself. So in other words, this include line per last week is a little bit of a hint. It's a teaser to Clang that you're about to see and use this function somewhere. But if you actually want to use the zeros and ones that CS50 wrote some time ago and bake those into your program, so your program actually knows how to get input from the user, well, then I'm going to have to go ahead and run a slightly different command. So let me do this. Let me clear my terminal window just to get rid of that distraction. And let me propose now that we run this command instead. Almost the same as before, Clang -o, space hello, then hello.c, but with one additional command line argument at the end. And this is a -l, not a number 1, so -l CS50 with no space in between those two. Now, the L is going to result in all of those zeros and ones that actually were written by CS50 being linked into your code, your few lines of code or mine here. But that's the second step that the compiler requires in order to know how to actually execute and rather compile your code and CS50's. And CS50 is not the only one that does this. If you use any third-party library in C that doesn't come with the language, you would do -l such and such, where however they've named their own library. But you don't have to do it for built-in things like we've been using thus far. All right, so let me go ahead and try this. I'll go back to VS Code here, and let me go ahead now and run clang -o, hello, then hello.c, and now instead of just hitting enter, -l CS50 with no space between the L and the CS50, enter. Now nothing bad happens, and now I can do /hello. What's your name? I'll type in David, enter, and now we see hello, David. Now, honestly, this is where we're really getting into the weeds. And now this is really just adding nuisance to the process of compiling and running your code. And so the reality is, even though this is indeed what is happening, this is why we used last week, and we're going to continue using this week onward, make, because it just automates that whole process for you. But it's ideal to understand what's going wrong, because any of the error messages you saw for problem set 1, any of the error messages you see for the next few weeks, probably aren't coming from make. They're coming from clang underneath the hood, because make is just automating the process. But with make, you literally just write make and then the name of the program. You don't have to worry about any of those command line arguments. Questions then on compiling with -l CS50 or anything else? Yeah? Sorry, what is the benefit of? What is the benefit of using clang manually? None really. In fact, all make is doing is saving us some keystrokes. If you prefer, though, and you just like to be more in control, you can totally run clang manually if you remember the various command line arguments. Yeah? Exactly. Why did I have to explain, that is, provide a hint to CS50 with the CS50.h header file, but I didn't have to do that with standard.io.h? Just because. Standard.io.h comes with C, just like a few other libraries come with C that we'll start seeing today. CS50, though, is not built into C everywhere, and so you do have to explicitly add that one there. Yeah? A command line argument is a word or phrase that you type at the command line, aka your terminal, in order to influence the behavior of a program. Yeah, it changes the defaults, right? In our GUI world, graphical user interface, you and I would probably click some boxes. We would select some menu options to configure a program to behave in the same way. At a command line interface, you have to just say everything all at once, and that's why we have command line arguments. Yeah? No, make is not just for CS50. It's used globally in any project really nowadays using C, C++, even other languages as well. In fact, most every command you see in this class, unless it has 50 at the end of it, is globally used. Only those suffixed with 50 are indeed course specific. And even those will gradually take training wheels off of so that you know exactly what those commands are doing as well. All right, so what is it that we've just done? Everything we've just done, of course, I keep calling compiling. But let's just go down one rabbit hole so that you understand that when you compile code, there's actually a whole bunch of steps happening. And this is going to enable a lot of features, like companies can write code and then convert it to run it on Macs and PCs alike, or phones or the like. So it's not just a matter of converting source code to machine code. There's actually 4 steps involved in what you and I, as of last week, know as compiling. And these aren't terms that you'll have to keep in mind constantly, because again, we're going to abstract a lot of this away. But just so we've gone down the rabbit hole once, let's consider each of these 4 steps that have been happening for you for a week automatically. The first of which is called pre-processing. So what does this mean? Well, let's consider that same program as before. Notice that 2 of the lines of code start with a hash mark. That is a special symbol in C, and it's a so-called preprocessor directive. You don't need to memorize terms like that, but it just means that it's a little different from every other line. And anything with a hash symbol here should be preprocessed. That is, analyzed initially before anything else happens. So let's consider these 2 lines up top. What exactly is happening? Well, it turns out with these 2 lines, you have 2 header files, of course, CS50.h and standard.io.h. Where are those files? Because they've never been in VS Code for you, seemingly. If you type ls, if you open up the File Explorer in the GUI, you have never seen probably CS50.h or standard.io.h. They just work. But that's because there's a folder somewhere on the hard drive that you're using on your Mac or PC or somewhere in the cloud, as in our case. And inside of this folder, traditionally called /user/include. And user is deliberately misspelled. It's just slightly more succinct, although it's a little weird why we dropped that one letter. But user/include is just a folder on the server that contains CS50.h, standard.io.h, and a bunch of other things as well. So in fact, if you type in VS Code in your terminal window, when you're using code spaces in the cloud and type ls space /user/include, you can see all of the files in that folder. But we've pre-installed all of that stuff for you. So let's consider what's actually in those files here, where if I highlight these two lines up top that start with #include, well, I kind of hinted last week that what's in that first file is a hint as to what functions CS50 wrote for you. So you can kind of think of these include lines as being temporary placeholders for what's going to become like a global find and replace. That is, the first thing Clang is going to do, it's pre-process this file. It's going to look for any line that starts with #include, and if it sees that, it's going to essentially go into that file, like CS50.h, and then just copy and paste the contents of that file magically there for you. You don't see it visually on the screen, but it's happening behind the scenes. And so really, what's happening with this first line is that somewhere in CS50.h is the declaration of getString, like we talked last week. And it probably looks a little something like this. And we didn't spend much time on this yet this past week, but we will in time more. Notice that this is how a function is declared. That is, it is decreed to exist. The name of the function, of course, is getString. Inside of the parentheses are its arguments. In this case, there's one argument to getString, I claim today, but you've known this implicitly. And it's a prompt. It's the prompt that the human sees when you use getString. What is that prompt? Well, it's a string of text, like quote unquote, what's your name, or anything else that I asked last week. Meanwhile, getString, as we know from last week, has a return value. It returns something to you, and that too is a string. So again, this is also called a functions prototype. It's the thing toward the end of last week that I just copied and pasted from the bottom of my file to the top, just so that it was like this teaser for Clang as to what would exist later. So you can think then of these include lines as just kind of combining all of those function declarations in some separate file called CS50.h so that you yourself don't have to type them every time you use the library. Or worse, so that you yourself don't have to copy and paste those lines. This is what Clang is doing for you in its first step of pre-processing. Second and last in this example, what happens when Clang pre-processes this second include line? Well, the only other function we care about in this story is printf, of course, which comes with C. So essentially, you can think of printf's prototype or declaration as just being this. Printf is the name of the function. It takes a string that you want to format, like hello, comma, world, or hello, comma, %s. And then with ... this actually has technical meaning. It means, of course, that you can plug in 0 variables, 1 variable, 2, or 10. So ... means some number of variables. Now, we haven't talked about this yet, and we won't really in general. Printf actually returns a value, a number, that is an integer, but more on that perhaps another time. It's generally not something the programmer tends to look at. But that's all we mean by pre-processing, so that at the end of this process, even though there's more lines of code in CS50.h and standard.io.h, what's really just happening is that Clang, in pre-processing the file, copies and pastes the contents of those files into your code so that now your code knows about everything. getString, printf, and anything else. Any questions then on that first step, pre-processing? Yes? Good question. When you include a file, does it only include what you need, or does it include everything? Think of it as including everything. So if it's a big file, that's a lot of code at the very top. And that's why, if you think back to all of the zeros and ones I showed a little bit ago, as well as last week, there's a lot of zeros and ones that end up on the screen as a result of just writing hello world. A lot of those zeros and ones are perhaps coming from code that you didn't actually necessarily need. But some of it is perhaps there. But there are ways to optimize that as well. All right, so step 2 of compiling is confusingly called compiling. It's just this is the term that most everyone uses to describe the whole process instead of just this one step. But once a program has been pre-processed behind the scenes by the compiler for you, it looks now a little something like this. And I've put dot, dot, dots just to imply that, yes, to your question, there's more stuff above it, there's more stuff below it. It's just not interesting right now for us. So now we have just C code. There's no more preprocessor directives. At this point, all of the hash symbols and those lines of code have been preprocessed and converted to something else. And so now, and this is where things get a little spooky looking, here now is what happens when Clang or any compiler literally compiles code like this. It converts it from this in C to this in assembly code. So this is among the scarier languages. I myself don't really have fond memories. This is not a language that many people program in. If you take a subsequent class in computer science, in systems, a higher level class, you might actually learn this or some variant thereof. But there's at least a few people out there that need to know this stuff because this is closer to what the computers themselves nowadays understand. Like the Intel CPUs or the AMD CPUs, the brains of today's computers and phones, understand stuff that looks more like this and less like C. Now, it's completely esoteric, but let me just highlight a few phrases. There's some stuff that's a little familiar. There is mention of main at the top there in yellow. There is mention of getString toward the bottom. There is mention of printf down below. So this is just another programming language called assembly language that decades ago humans, myself included in school, did write code in. And absolutely, some people still write this code, especially since you can write very, very efficient code. But it's a lot more arcane. It's a lot less user-friendly. So you'll see in yellow now, these are the so-called instructions that a computer's brain or CPU understands. Pushing values around, moving them, subtracting values, calling functions, and move, move, move. So really, the low-level operations that computers understand tend to be arithmetic operations, subtraction, addition, and the like, moving things in and out of memory. It's just a lot more tedious for folks like us to write code like this. This is why you and I tend to write stuff like this. And ideally still, people like you and I tend to drag and drop puzzle pieces that sort of abstract all of that away further. But for now, this is again called assembly language. It is what happens when the compiler literally compiles your code. But of course, this still not zeros and ones. So we got 2 steps to go. So when a compiler proceeds to step 3, this is where things get converted to machine code. And when a compiler assembles your code for you, it converts what we just saw on the screen here to actual zeros and ones, the so-called machine code that your phone or your computer understands. But it's worth noting that these are not necessarily all of the zeros and ones of your program. Yes, they are the zeros and ones that correspond to your hello program or printf and getString and the like. But notice that here we need one final step. In those zeros and ones are only your lines of code. But what about CS50's lines of code that we wrote to implement getString? What about the lines of code that humans wrote decades ago to implement printf? Those are somewhere on this hard drive, like on my Mac, my PC, or somewhere in the cloud. But we need to combine all of those zeros and ones together and link my code with CS50's code with standard IO's code all together. And so what happens in the last step ultimately is that if we have my code here in yellow, and then the code that CS50 wrote, and the code that the authors of C itself wrote, what really is happening is that somewhere we have not only hello.c, which obviously I wrote and wrote with us live here. There's also, let's assume, somewhere on the computer a CS50.c file that coincidentally I and CS50 staff wrote years ago. And also somewhere on the computer there's another file. Let me oversimplify by just calling it standardIO.c. In practice, it's probably specifically called printf.c. But there's somewhere these 2 other files. And so this last step called linking takes my zeros and ones from the code I just wrote, namely this code on the screen here. It then grabs the zeros and ones that CS50 wrote, and it grabs the zeros and ones that the authors of C wrote in order to implement the standard IO library. And lastly, voila, links them all together. And this is the same blob of zeros and ones that we saw earlier. It's just now the result of pre-processing your code, compiling your code, assembling your code, linking your code. And my God, at this point, like if there were any fun in programming for you yet, we've just taken it all away. we just call this whole process compiling. Why? Because now that we know those steps exist and smart people solve that problem for us, you and I can kind of operate at this level of abstraction and just assume that compiling converts source code to machine code. Questions, though, on any of these intermediate steps? Yeah?
For linking, like, are they like the different parts, like for example, Studio and CS50 and your own parts, are they stored in different places? Like what these have to be like all around?
A good question. So where are all of these zeros and ones stored? Because you and I, we've been using a browser. At code.cs50.io, of course, is this web-based user interface. But again, recall from last week, even though you're using a web browser to access VS Code, that web-based version of VS Code is connected to an actual server somewhere in the cloud. And on that server, you have your own account and your own files and really your own hard drive virtually in the cloud. Think of it a little like Dropbox or Box or Google Drive or OneDrive or something like that. So you have a hard drive somewhere out there that we've provisioned for you. And it's on that hard drive that we have your code that you just wrote, or I just wrote, CS50.c, standard.io.c, and all of the other code that implements the math functions and everything else that C supports. Good question. Yeah?
So say the CS50 library, the line counting included, is that do the same exact thing if I went to the CS50.c and copy pasted all the library?
Good question. That hash includes CS50.h line at the top of my code. If I just replace that with the contents of CS50.c, would that work? Short answer, yes, that would work. You could copy all of the code there. However, there's some order of operations that might come into play. And so it's probably not quite as simple as copy paste. But conceptually, yes, that's what's happening. Now, with that said, in CS50.h are only the prototypes of the functions, the hints as to how the functions look, what their return type is, what their name is, and what their arguments are. It's in the .c file that actual code tends to be written. And this is a little confusing now because you and I have only written code in .c files. But in the next few weeks, you'll actually start writing some of your own .h files as well, just like CS50, just like standard.io. But in essence, that line of code just makes it easier to use and reuse code that's already been written. And that's the whole point of a library. I say that a little louder? Yes. Does linking happen when you compile your code? Yes. When you run make, as we have been doing the past week now, all four of these steps are happening. Preprocessing converts the hash include lines to something else. Compiling technically converts it to assembly code, which the Mac, the PC, the server more closely understands. Assembly converts that language to binary, machine code that this computer actually understands. And then linking combines everything together. And in fact, if you think back a few minutes ago to when I did this -L CS50, the reason I had to add that and the reason my code did not compile at first was because I forgot to tell Clang to link in CS50's zeros and ones per that last step. I don't need to do -L standard.io because it comes with C. So that would just be tedious for everyone in the world. But CS50 does not come with C, so we link that in. And to be clear, too, we won't always use CS50's library. That'll be yet another pair of training wheels we take off in the coming weeks. But for now, it makes a few things simpler. Yeah? Short answer, yes. So what do the zeros and ones, the machine code, translate to? Yes, there is a one-to-one relationship between the machine code and the assembly code. Assembly code, it's not really English, but at least it's symbols I recognize. It's not zeros and ones. Machine code, of course, is just zeros and ones. So back in the day, before C existed, people were programming only in assembly code. Before assembly code existed, people were coding in zeros and ones. And you can imagine just how painful that was. And so each of these languages makes life for us sort of easier and easier. In a few weeks, we'll transition to Python, which will in turn make C even simpler, or coding in general simpler to do too. All right, so with that said, what now can we, what could go wrong with this? Well, it turns out that besides compiling, technically speaking, there's decompiling. And we've not done this, and we won't do this. But it's worth considering for just a moment. If you were to not compile your code, but decompile it, as the word suggests, this just means reversing the process. Converting it, ideally, from machine code, zeros and ones, maybe back to C. Now, this would be cool, perhaps, if all you have is a program. You could convert it and see the actual source code. What might a downside be if anyone on the internet is able to decompile code on their machine? Yeah. OK, so it's easier to find bugs in the code to exploit. So it might be easier to hack into the software by finding mistakes you and I made, because literally they're staring at you in code, whereas the zeros and ones make it way less obvious. Other downsides of what I call decompiling? Yeah.
If stuff is copyrighted or people don't want people to know how you did it.
Yeah. Yeah, if your code, your work is your intellectual property, copyrighted or otherwise, that's kind of obnoxious that someone can just like run a command and boom, they can see the original code that you wrote. Now, it turns out it's not quite as simple as that. And so even though, yes, you could take a program like Hello or even Microsoft Word and convert it from zeros and ones back to some form of source code, be it in C or Java or Python or something else, whatever it was originally written in, odds are it's going to be an utter mess to look at. Why? Because things like variable names are not retained in the zeros and ones typically. Function names might not be retained in the zeros and ones. The code is, the logic is, but the computer doesn't care what pretty variables you chose and how nicely named your functions were. It just needs to know them as zeros and ones. Moreover, if you think about last week, we introduced things like loops in C. And besides for loops, there's what other kind of loop, for instance? So a while loop. And even though they look different and you have to write different code, they achieve exactly the same functionality, which is to say, when you compile a for loop or you compile a while loop, if they logically do the same thing, they might end up looking identical as zeros and ones. And so therefore, it's not necessarily predictable that you'll get back the original code. Why? Because the zeros and ones might not know, so to speak, whether it was a for loop or a while loop. So maybe decompiling will show you one or the other. And honestly, decompiling, while possible, and it's one way of reverse engineering someone's product, odds are, if you're good enough to start reading code that's been decompiled and reading through the messiness of it, odds are you have the talent probably to just write that same program from scratch yourself. Now, that's an overstatement, perhaps, but it's not quite as easy or threatening as you might first think. So in general, once code is compiled, it's pretty challenging, time-consuming, costly to reverse engineer it, much like it would be in the real world, right? Like all of us have some kind of phone probably nowadays in our pocket. There's nothing stopping you from opening it up somehow, poking around, recreating what's there. That's a huge amount of effort, most likely. And at that point, maybe you should just invent a phone instead of trying to reverse engineer it. So same kind of idea in the physical world. Any questions then on compiling or even decompiling in these forms?